Hi everyone, this is Dr. D. Amsaveni, Associate Professor, PG and Research Department of Mathematics, Sri Sharada College for Women, Salem. In this video, we will understand the Uniform Boundedness Principle. The Uniform Boundedness Principle or Uniform Boundedness Theorem, also known as the Banach-Steinhaus theorem, which is a fundamental result in functional analysis. This theorem is a cornerstone of fundamental analysis, providing a crucial link between pointwise boundedness and uniform boundedness. This theorem has significant implications in various areas of mathematics, including operator theory, functional analysis, and signal processing. It helps in characterizing the properties of Banach spaces and plays a role in proving certain pointwise convergence results for Fourier series. It states that if a sequence of bounded linear operators between Banach space and norm-linear space is pointwise bounded, then it is uniformly bounded. This means that a sequence that is bounded for every input must also be bounded as a whole. So here the uniform boundedness theorem stated mathematically. Before that, we will understand about the concepts of pointwise boundedness and uniform boundedness. Pointwise boundedness means the family of operators is bounded at each individual point. Uniform bounded means the family of operators is bounded uniformly for all points. Mathematically, these notions defined as follows: a set script f of bounded linear operators from a nonlinear space X into nonlinear space Y is said to be pointwise bounded if for each X belongs to X, the set Tx, but T belongs to the set script F is bounded set in Y. For each x belongs to X, Tx is a bounded set in Y. Uniformly bounded if script F is bounded set in the normed space P of xy. Lies the boundedness of the set script f in the normed space B of x comma y implies that there exists a constant k greater than 0 such that norm t is less than or equal to k for every t belongs to script f. So now let us see uniform boundedness theorem. The statement is here: let B be a Banach space and N a norm-linear space. B be a Banach space, N is a norm-linear space if Ti is a non-empty set of continuous linear transformation B to N, linear transformation of B into N with the property that Ti of X is bounded subset of N for each vector X in B. For each vector X in B, Ti of X is a bounded subset of N. Then you have to prove that norm Ti, the set collection, the set Ti is a bounded set of numbers. That is, the set Ti is bounded as a subset of script B of B comma N. That is the set of all continuous linear transformations from B to N. Let's see the proof of uniform boundedness theorem. Let B be a Banach space and N be a normed linear space and the set Ti be the set of all continuous linear transformations of B into N. Now, for any natural number n, we define a set we define a set f n is equal to set of all x such that x belongs to B and norm Ti of x is less than or equal to n for every I. First we show that this Fn is a subset of closed subset of B and let S of 0 comma n be the closed sphere with center 0 and radius n in capital N. Let x belongs to capital N if and only if, by the definition of Fn, we have norm Ti of x is less than or equal to n for every I. If and only if, this means that Ti of x belongs to S of 0 comma n for all I. If and only if x belongs to Ti inverse of S of 0 comma n, and only if x belongs to intersection or I Ti inverse of S of 0 comma n. Therefore, Fn is equal to intersection I Ti inverse of S of 0 comma n. That means intersection of closed sets. Intersection of closed sets. Therefore, Fn is closed. So we proved that Fn is a closed subset of B. Further, Further, we can write B is equal to union n is equal to 1 to infinity Fn. Suppose that B is not equal to union n is equal to 1 to infinity Fn. Then there exists x belongs to B such that x does not belongs to Fn for any n. Since B is not equal to union Fn, then there exists x belongs to B such that x does not belongs to Fn for any n. This implies, by the definition of Fn, norm Ti of x is greater than n for that x belongs to B. So this is a contradiction to the fact that Ti of x is bounded because we assume that each Ti is bounded. So this is a contradiction. This is a contradiction to that Ti of x is bounded. Hence, B must be equal to union n is equal to 1 to infinity Fn. That is, the complete space, that is, the complete space B is the union of sequence of its closed subsets. Then, by Barre's theorem, there exists an integer n naught such that f n naught bar has non-empty interior. Since this fn naught bar, since fn naught bar is closed subset of B, we have Fn naught is also a closed subset of B. Therefore, Fn naught bar is equal to Fn naught. That implies Fn naught has non-empty interior by the Barre's theorem. That is, interior Fn naught is not equal to empty. Then there exists some x naught belongs to Fn naught such that Fn naught is a neighborhood of x naught by the definition of interior. Since Fn naught is closed, already we have discussed Fn naught is closed, there exists a closed sphere S of x naught comma r naught with center x naught and radius r naught such that S of x naught comma r naught is equal to the set of all x belongs to B such that norm of x minus x naught is less than or equal to r naught, which is a subset of Fn naught. Let x belongs to B be arbitrary and x not equal to 0. And let us take z is equal to x naught plus rx, where r is equal to r naught by 2 into norm x. We take z is equal to r naught plus rx, where r is equal to r naught by 2 into norm x. Then norm of z minus x naught, z minus from this, z minus x naught is equal to Rx, and we take norm here, which is equal to R into norm X, which implies norm Z minus X naught is equal to, we substitute R is equal to R naught by 2 into norm X into norm X, and then we will get R naught by 2. So definitely it will less than R naught. Z minus X naught is less than R naught. So Z belongs to S of X naught comma R naught. Implies Z is equal, Z belongs to Fn naught. Therefore, therefore, T norm Ti of Z is less than or equal to N naught for each I. Since the point Z is in Fn naught, the definition of Fn naught, Fn already be defined there. So by the definition of F naught, we have norm Ti of Z is less than or equal to N naught for each I. Since x naught belongs to S of x naught comma R naught, we have norm Ti of x naught is less than or equal to N naught for all I. Now, Z is equal to x naught plus Rx. We take here Z is equal to x naught plus Rx. From this, x is equal to Z minus x naught by R. Taking the linear transformation both sides, so Ti of x is equal to Ti of Z minus x naught by R for each I, implies norm, apply the norm on both sides. and then we will get 1 by r into norm ti of z minus x naught. It is less than or equal to 1 by r into n naught plus n naught. So ti of z already here, it is less than or equal to n naught, and ti of x naught is also n less than or n naught here. Ti of x naught is less than or equal to n naught. Therefore, norm ti of x is less than or equal to 1 by rn into n naught plus n naught. It is equal to, substitute r is equal to r naught by 2 into norm x. So 1 by r is 2 into norm x by r naught into n naught plus n naught is 2 n naught, and implies ti of x is less than or equal to 4 n naught by r naught into norm x for each I, which implies t norm ti of x less than or equal to c into norm x for each I, where c is equal to 4 n naught by r naught, and this can be written as norm ti into norm x less than or equal to c into norm x, implies norm ti is less than or equal to c. Norm x cancel. Therefore, norm ti is a bounded set of numbers. That is, the set ti is a bounded as a subset of script b of b comma n. That is the set of all continuous linear transformations. Therefore, we have proved. Thank you.